last year we had Professor Ashok Sen talking about the age of universe. So it's only appropriate that we talk about what more about universe. I'm sure the black night sky must have intrigued human beings and like nothing else has ever done. So from something up there to why and what is up there, human inquisitiveness and scientific knowledge have come a long way in exploring the hitherto unknown. From the naked eyes raising eyebrows through Cassini's wide-angled camera to James Webb Space Telescope's infrared detectors, exploration of space, I'm sure, has certainly been more exciting and intriguing than anything possibly else. Wispy clouds of gas, the strange super bubble dominating the view of the recent Hubble Space Telescope image to the nebula, the gas cloud, the hydrogen gas glowing in the dark, along with dark dust lens of stars of all ages. The JWST image revealing a cluster of never seen before young stars at the center of the image that was previously shrouded by dust. If this do not mesmerize you, I do not really know what possibly can. Also, please have a look at the latest capture of Jupiter by JWST. They say beauty lies in the eyes of the beholder, and we feel so fortunate to have an eminent beholder along with us, Professor P Sreekumar. Let's see the space through his eyes. So may I request Professor P Sreekumar to please join us on the dais, and I also request our officiating director, Professor A Srinivasan, to accompany him. I request Professor A. Srinivasan to kindly greet the speaker of the day with a flower bouquet. Well, Professor P. Sreekumar is an astrophysicist by training. Till January 2023, he was the Satish Dhawan Professor at ISRO and advisor to the Space Science Program Office at ISRO headquarters, and is currently the director of Manipal Center of Natural Sciences. After obtaining his BSc from the University of Kerala and MSc in Physics from the Indian Institute of Technology, Bombay, Professor Sreekumar pursued his PhD research on gamma ray astronomy at the University of New Hampshire, USA. His postdoctoral research focused on the emerging areas of observing the universe in gamma rays using NASA's Compton Gamma Ray Observatory. After a decade at NASA's Goddard Space Flight Center, he joined ISRO in 1999 to head the astronomy division at the ISRO Satellite Center. In 2013, he went on deputation from ISRO as a director of Indian Institute of Astrophysics. In 2018, he returned to ISRO headquarters as the director of Space Science Program Office until his superannuation in 2020. A few more words about his contribution to space science in India. Professor Sreekumar is the co-PI of India's first dedicated astronomy observatory called AstroSat. He has been the principal investigator of payloads on Lunar missions and currently participates as member and chair of many review committees linked to space science missions of ISRO. He has contributed to the design and development of space payloads of Chandrayaan-1 as the PI. Professor Sreekumar's primary research interest varied over the years from the study of gamma rays to X-rays from cosmic sources, composition of sun's corona, to mapping of chemical elements on the lunar surface. As an experimentalist, his most recent involvement was in the design and development of X-ray mirrors for future space use. With interest and expertise in the areas of astronomy and astrophysics, planetary science, and space instrumentation, Professor Sreekumar has contributed immensely to the areas of gamma ray and X-ray astronomy, space instrumentation design, star formation studies, and X-ray optics development. His current interest is on the development of multi-layer mirrors for X-ray polarimetric studies. He is also a part of many senior level management committees of international programs with Indian collaborations, including the LIGO India program, the SKA India, and the India TMT programs. Awards and recognitions bagged during his illustrious career include many. Let me share a few with all of you. National Science Talent Scholarship in 1976, NASA Group Achievement Award in 1991, NASA GSFC Special Act Group Award in 1992, University Space Research Association Scientific Excellence Award in 1993, Vikram Sarabhai Award for Space Science in 2003, Chandrayaan-1 Payload Team Award in 2001. So with the successful launch of Chandrayaan-3 and Aditya L1 at the backdrop, I do not really think we can get a better occasion and speaker to talk about space explorations. With a round of applause, let's please welcome Dr. Sreekumar to do what he does the best. Well, I don't really think we can thank him enough for being along with us in such a short time. So on behalf of the entire NISER community and on my personal behalf, I extend a warm welcome to you. The floor is all yours, sir.
Good afternoon. Thank, thanking Director NISER, Professor Litton, and others who encouraged me to come here. I've been planning to come to NISER for some time. My interactions with NISER have been with a few colleagues in the Earth and Planetary Department. And so it's a pleasure to come to NISER. NISER is a place where we see science emerging out of the youth of the country. And science, the absence of science has been a matter of concern to anybody involved in large projects today in India, including the mega projects, including science, ISRO's space science missions. There's a real need to really encourage and bring in innovative thinking and potential scientists from the younger crowd. And I think NISER today plays a very important role in doing that. So I'm very happy to be here on this Foundation Day and to honored to be asked to give this lecture. So I thought I will initially had another title, but then I think Director indicated you should say some things about the current missions as well. So I slightly changed to say exploring our solar neighborhood and beyond, technology critical science, and let's see what that evolves into. You may feel free to stop and ask me questions in the middle or at the end. Either way is fine with me. So let me begin with a discussion on access to space itself. It is not too long ago that we had access to space because 57 is not a long time in the context of those who study Earth and the universe. But as soon as a Sputnik as a satellite went up, we have a capacity to get into space, and access to space was available, and very quickly in a very short time. Today it's very hard to comprehend how in about 4 years' time you managed to get a human being into orbit. I mean, extremely challenging task, but they did it maybe with high risk. And then in '69, we actually had people land on the moon, and there are exciting stories about how they managed to do it. And but then after the initial spur of human exploration of the moon and the challenge between the Soviet Union and America sort of slowly died down, there were exciting set of experiments where the desire to really explore the universe was at the forefront, and you could actually use instruments and machines to explore the solar system and beyond. And we had these exciting programs of Pioneer and Voyager, small experiments that really went very far. And There's a very interesting story on the internet. If you look 1977, I think a student at JPL or maybe at Caltech, I don't remember, a PhD student actually came up with this idea that 1977 provides a very unique opportunity to actually fly a spacecraft that can actually traverse outer solar system and actually visit many of the planets with minimal energy. And that opportunity comes more than 150 years later, the next opportunity. So there was a real desire to exploit this in the early 70s. At JPL, there was a big effort to do it. They lost out, etc. Finally, mid 70s, I think mission was back in, and the Pioneer and Voyager missions actually evolved in that fashion. And today we can see exciting results where they visited outer planets. They got the first views on Jupiter, Saturn, Uranus, and Neptune, and then went on to really explore the regions of space where the edge of the heliosphere, the region where sun and its solar wind actually sweeps up material, and the edge of the solar system was seen. And the Voyager mission actually slipped through that, and you could actually see that issue. So the whole idea of exploring the space beyond Earth had an entirely different perspective at the end of these set of missions, Pioneer and Voyager missions. In the 80s, again, there was an evolution of this system where you said, okay, humans need to get into space. And Americans had this the space shuttle program where you could actually people can land back, and the presence of a space station happens. Of course, there are many space stations, etc. And today, there's an International Space Station that shows a collaborative location in space where many countries can participate, do experiments connected to microgravity conditions or simulate conditions that are not available on Earth for the pursuit of science and technology. And now in 2020s, you also had this scenario of private industry, private companies actually being able to do things that was quite unimaginable sometime back, that they could take on programs of this magnitude. So there's been a fair amount of progress in this, and I also show this little picture here that was carried in the early Pioneer and some version of it in Voyager. And those who have seen it will remember how unique it is to really design a picture to another civilization, to tell them about who we are, where we are, and how do you convey that message. And there is a lot of story in it, and those who haven't studied it, I would urge you to really look at it. Just to take an example, the two circles at the top represent two atoms of hydrogen. And that separation is actually telling you, it is actually talking about a radiation that comes from hydrogen. The simplest radiation that comes from hydrogen is when the proton and the electron of a hydrogen atom, which under normal conditions have opposite spins, when with minimal excitation, with small temperatures, it can actually get excited where they become parallel. When it de-excites, it emits a radiation whose wavelength is 21 centimeters. It's also seen as 1.4 gigahertz. So the 21 centimeter is represented in this little bar. And that's a scale against which we can actually talk about the size of a human being and so on. So a lot of clever thoughts that I think Carl Sagan and a bunch of people actually put together. You should really study it because it tells you about how humans on Earth would one day attempt to communicate regarding where we are and who we are, etc., to an entirely different civilization. So this is the early phase of it, and then so this space platform that was actually created, we've been primarily using it to study the cosmos, solar system in particular. We also look back at Earth and use it to study Earth. And today, a huge program in India, an Indian Space Research Organization, is really looking at Earth with regard to using remote sensing. It's probably the world's best remote sensing program, where these data are actually fed back into decision-making processes using products that have been processed at various levels. So that is a very important part of using space platform for Earth studies. And of course, the potential to really look at it as we look at humans going beyond Earth, both in terms of astronauts, tourists, establishing bases on the moon, and so on. There are new areas that have to be addressed. And so the presence of humans in space is going to drive the need for plants that grow, plants that are nutritious, plants that require very minimal inputs to survive, plants that can survive radiation of space and so on. And of course, there is this overall effort to look at material research in zero gravity. So the key scientific problems that were of interest would be in terms of the nearest object, the moon, its origin, how it evolved, and then the connection to the nearby planets of Venus, which is similar to Earth, but has gone a completely different way with regard to its temperature and atmosphere. So the comparative study of Earth, Venus, and Mars is a very important thing. Planets have migrated. The solar system as we knew it wasn't the way it was, and there are colleagues at NISER who study this thing, and it's very important to understand how these migrations took place. Comets, which are a critical part of bringing water to many of our planetary surfaces, potentially even life on Earth, which we do not know, but people talk about it. But the origin of these comets need to be understood, and there is clearly a lot of excitement in actually looking at comets, whether comets actually have brought water to the poles of the moon, and maybe later when we discuss it, we can have a little bit further discussion on that point. Sun's influence on the planet is critical. The star-planet interaction is very critical, both for the solar system as well as those who are studying exoplanets. People here are studying exoplanets, and you want to really understand the connection between stars activity and habitability of these planets. So the solar system provides us an avenue to study it. There are powerful processes that happen in our galaxy when you have stars that are not single but binary stars. I mean, a good fraction of the stars in our galaxy are binary stars, where they have gravitationally they're bound to a common center of mass. They go around each other, and when they go around each other, there are some very interesting behaviors that happens. It transfers sometimes, in some cases, mass from one star to the other star, and that process of accreting that material into the center of a compact star, a very dense star like a neutron star or a black hole, creates what are called accretion disks. And these accretion disks actually are places where you convert gravity, as we know it, Newton's law of gravity into energy in the form of radiation. So you actually are transforming gravitational energy into radiation, and it does it with an efficiency that is many times more than the most efficient process we know in nature today, and that is nuclear fusion on Earth. So accretion processes actually produce even greater efficiency with regard to converting mass into energy. So studying these objects are critical, and of course the larger questions about the formation of many cosmic objects like black holes, transients, things that are there for short periods of time, they undergo episodic activity, and so these are all areas where we use space as a platform to pursue these studies. So now let me just turn a little bit for a few minutes to the India's lunar exploration program, and we've been having a lot of press coverage and in newspapers on moon because of our current missions. But behind all of that is still continuing the desire to understand the origin of the moon, how it actually happened. Is a theory that says that a giant object of the size of Mars struck Earth, out of which moon formed, and if so, how do we understand more about it, etc. Sorry. Unlike Earth, which has an atmosphere, Moon's absence of atmosphere makes it very unique with regard to preserving the signatures of early events in the early part of the solar system, collisions, of impacts of large bodies, asteroids, etc., leave craters, which there were craters on the Moon, on Earth as well, but Earth being a more dynamic planet with water, rain, wind, actually things are hidden. Whereas the moon is preserved. So the moon is a great place to really study the early history of Earth. And of course, as human beings, we always like to go, we have an inquisitive mind to really explore what is in the neighborhood, what's on the other side of the fence. You want to see it. So we really need to explore that. And that is also to be kept in mind as we talk about exploration programs in the country. Not just pure science, it's also the very fact that as humans, we often desire to learn, and moon could also become a potential place for resources for future exploration. That is something I'll come to towards the end of the talk. And so the journey to moon is not simple because of the fact that Earth has a magnetic field, and the magnetic field does something good as well as bad. The good thing is, as residents on Earth, we are protected from the intense radiation of particles and fields that come from Earth, from the sun. The sun undergoes occasional rearrangement of its magnetic field and gives rise to what are called solar flares. And at that time, most often it also releases a lot of plasma in the form of a huge plasma blob, which we call as coronal mass ejections. These have primarily protons, alpha particles, electrons, and they sweep into the path of the Earth. But the Earth's magnetic field protects us, except for maybe the polar regions where you are subjected to this additional radiation. However, as potential visitors to the moon, if you want to go to the moon, you have to cut through this trapped radiation belt. And so you need to worry in terms of damage to yourself, etc. Even when you have an experiment on a mission, on a lunar mission, you worry about how many times do you have to cross the radiation belt, because that in turn can affect the performance of your system because of radiation damage. But clearly a matter of concern for humans, and so which is part of the reason why the Apollo astronauts didn't hang around Earth for too long. They went straight to the moon. They want to work quickly and come back, because the sun does something crazy at that time, they could have been in trouble. But given the tremendous pressures politically, they took extreme risk in actually heading off to the moon in one go. So the moon is about 60 times Earth's radius away, so not very far. But unlike Earth's large tilt angle, it only has a very tiny tilt angle, which actually has some important significance at a later stage. So as I mentioned earlier, there are craters on Earth. This is the one in Australia, northern Australia, Wolf Crater, just about a kilometer long. There are many such examples of impact of asteroids on Earth. However, on the moon, if you look, there's plenty of examples. And you age the location on the basis of crater density. Older places will have greater crater density compared to younger places. So we see that. And so studying that, so clearly moon gives us a great opportunity to understand the early impact processes. And this, as we discussed earlier, is just a model, computer model that shows, there have been many, is one of the more recent ones that actually shows, yes, you can form a moon-like structure with a high velocity impact of a large body on early Earth. The crust just comes off and then recoalesces back to form the moon. And hence we see a lot of similarities between moon and Earth, because it's largely made up of material for the Earth itself. And if you look at the overall picture of the moon, there's a near side and the far side. These are places where we have either samples and Apollo and human presence there. Some cases, automatic machines went and landed there. And then we had the recent landing of Chandrayaan-3 at a pole, not actually to the pole, but it's actually polar region. So it's not the pole. It's important that we understand that. And the press has often said we landed at the South Pole. We didn't land at the South Pole, polar region. It has importance because of the fact that much of what we know in terms of samples, etc., are primarily from the central region of it. So there could be variations, and there is a larger theory of how volatiles on the moon migrate to the poles, from the numerous heating and cooling cycles that happens as the moon rotates. So there is this desire to really look at higher latitudes away from the equator and ask, are the soil conditions, the composition, etc., different from what you see at the poles? Because that is a way to really predict what you may see at the poles as well. So much of what we know comes from samples that have been returned, and as from lunar meteorites. These are examples of actual material that you have. And so back on Earth, you can study that in great detail. You have fantastic labs where you can do all of this stuff. Of this large collection of material that has been brought back, in particular the Apollo material, nearly half of it is still kept in storage. And it's kept in storage because we were waiting for better instruments to come around. I think they're preserved because it's so valuable. So very carefully preserved, and every year a small amount, tens of grams are released for people who write exciting proposals to really do something with it and so on. So Much of what we know is really coming from these samples that are there. Very recently, China added additional samples from a new site. And then there were, of course, from the Apollo missions when people were there, and they moved on buggies that could take them far away. You could actually have some localized sampling of various lunar materials. And then the automatic missions that were there using rovers and landers. There are in situ measurements like the one we're now doing with Chandrayaan-3. But the remote sensing from an orbit continues because, remote sensing from an orbit allows you to look at the global properties of a planet. And on a planet like the moon, the best way to really study that is to use a polar orbit where the orbit actually is inertially positioned in space, and the moon rotates under that. And so you actually continuously sort of scan strips of the moon, and over some period of time, you prepare your global maps, and that is what Chandrayaan-2 is actually doing right now. Now, there was a renewed interest for the moon. There was a lull between the end of the Apollo era, and then interest in Mars came up, and again, sometimes driven by funding agencies' perspectives and government perspectives. But in the late 90s, again, early 90s, there was a renewed interest in the moon. And in particular, there was an exciting thought about looking for water. Till that time, there was a feeling that the moon was very dry. In the samples that were brought back didn't really show much evidence of water. And I think early part of the 90s, there were careful examination of certain crystals brought back, which showed embedded water, very high levels of parts per million, at the level of tens of parts per million, which suggested there could be locations of the moon where there is water might be trapped. And water was also a point of interest on Mars and Venus and poles of Mercury. So we've been looking for water everywhere. And a part of the reason is water, we believe, is an essential component to look for life. Life elsewhere is certainly one of the big questions we are asking. And so search for life means search for water, and water might tell you where life is. And but it never be the surface, it could be below the surface. So there are the satellites of Saturn and Jupiter where we are looking for potentially water, and because they show ejected you see water below the surface that occasionally erupts, and in Enceladus, for example. So the research for water on the moon became a point of interest, and to address this, we had various missions from various countries, JAXA, China, and the United States. And then we joined the group with Chandrayaan-1, which is only an orbiter. Chandrayaan-2 had an orbiter, plus a lander and a rover. Of course, as you all know, we couldn't successfully complete that process. The landing was not a soft landing. And with Chandrayaan-3, we managed to do that. And so that gives you a chance to really probe nearby locations, where you get ground truth at some level compared to what you see from an orbit. And that needs to be further expanded as we go to future missions, which includes a potential mission to the actual pole of the. Now, the pole of the moon has this very unique property. Now, going back to the first cartoon that I showed, the sun rays, even for Chandrayaan-3, landing location minus 69 degrees south, the sun is at a very shallow angle. You never see the sun rise beyond, say, 10 degrees or so, which means it casts long shadows. In a long shadow, it's very hard to maneuver, even to operate the rover, etc., because you need solar power to really keep systems running. As you go to the pole, this becomes more challenging. But what is more interesting is the fact that there could be poles. At the poles, there could be craters that are deep enough that it will not ever see sunlight, maybe for the complete 4 billion years. And if there was original water from impact of comets, etc., some of that water in the form of ice could still be there. And so these are often called the permanently shadowed regions of the moon. And they are at the poles. And there is a great interest in looking and studying this water, both for science as well as for those who are looking at using moon as a base to really move elsewhere. If you want to really think about rocket fuel using hydrogen, then that water source is required. If you need oxygen, that water source is required. So water becomes an important thing and the poles appear to be good places to go. And that is fortunately because of the fact that the moon is not is tilted at 23.5 degrees like Earth. Otherwise, the water would have been affected by solar radiation. So the proof of hydration on the moon was seen through a reflectance spectroscopy in infrared, kind of work that Guneshwar does here, where you look at solar reflectance, sunlight bouncing back, and which will show absorption features indicative of minerals and also of water. And using that in Chandrayaan-1, they prepared a map of the moon that actually showed there is water on the moon that's widespread, and it actually increases towards the pole. But it had certain limitations, and that was being addressed with Chandrayaan-2. This is the picture of a Chandrayaan-2 in the early phase of the at Sriharikota. And what it does, Chandrayaan-2 and 3, now 3 also added to it, it had a combined attempt to look for water on the moon, look for global mapping and composition studies, and then localize in situ measurements using the rover. So this was the original plan of Chandrayaan-2, now completed using 2 and 3 together. And in each of these cases, there was a great emphasis for in particular, looking at water from water ice, both at the surface, subsurface, as well as in the space above the surface, which we call as the exosphere, to really map and the distribution of water if it exists. And so the evidence of water was there from Chandrayaan-1, but then the spectral signature for water and infrared actually spreads over a broader wavelength range. So the earlier experiment that produces map actually had a cutoff closer to 3 microns, whereas its full spectral feature is not visible in 3 microns. So when we designed the indigenous infrared spectrometer for Chandrayaan-2, there was carefully, it was extended to go up to 5 microns to really enable us to not only pick up the full spectral signature, but also use extra spectral range to correct for thermal emission. That is also part of this thing. We have to subtract the thermal component to do it. So with that in mind, and making sure that we will be able to make concrete statements about water, the new experiments were designed differently. And that also includes a synthetic aperture radar, which not only, which was also, there was a synthetic aperture radar on Chandrayaan-1, but a single band. It was operating in S band, but with 2 band, you can actually do better. And so Chandrayaan-2 carried a 2-band radar. This is that spectral signature I was discussing. We are seeing this from Chandrayaan-2 data. After subtracting the thermal component, we are seeing clear signatures of water at 3 microns, water ice. It also carries good cameras, just to get an idea. It's really showing high resolution images. You can actually see fine structures that are visible on the surface, because a camera that was made for such purposes had a very small coverage band, but then high resolution. You could resolve things at 0.3 meters. 30 centimeter objects can be, single pixel will be of that scale. And that is finer than what is on any other mission in the past. And using that, the Chandrayaan-3 landing spot was actually imaged carefully, and that actually helped us to really plan the mission very well. Of course, we can't easily measure slopes, but you have to do that using other data that exists. But clearly, the presence of large boulders, big craters, etc., could be studied using the cameras on Chandrayaan-2. So the cameras on board Chandrayaan-2 were exceptionally good. And also, the synthetic aperture radar was able to, because it penetrates the surface, you can see below the surface, and you can actually see craters that were hidden at some level. So here is a case where these craters are not very visible, but actually very clearly visible in the form of radar images, because it shows roughness. The rough areas actually reflect radar at high levels, and so you can actually, from the enhanced radar reflectors, you can actually see hidden craters. You can actually see structure around the crater. It actually tells you the impact direction from which the collision actually happened. Some object came and smashed into it, produced a crater, and you can see ejector material, which are subsurface. So the power of using multiple sensors to really study the surface of the moon. You also do things with chemistry where you allow the solar radiation. Remember, the sun is a hot object. Though its surface temperature is only 6,000 degrees, it has a corona, and that is what Aditya L1 is supposed to do, asking the corona is hot. Corona is about 2 million degrees. We don't fully understand why the corona is so hot. And when the source of heat, source of energy is actually the center of the sun. But that is the mystery for Aditya to solve. But whenever it undergoes flares, solar flares, it produces a lot of X-rays. These X-rays are falling on the surface of the moon, and that in turn excites atoms on the surface of the moon. And then these excited atoms de-excite, and that produces radiation. So what you're seeing is a spectrum from that reflected fluorescence. So since every atom has a characteristic signature, you can actually tell precisely what is that element. It is very no different from when you go to a goldsmith or a gold shop and actually give some old gold. They tell you in a matter of, in a few seconds, how much copper is there, how much gold is there. They use X-ray fluorescence to really map it. You're doing something similar. The only difference is instead of a gold in the gold shop, you have actually a precise calibrated X-ray source sitting there. It's positioned at a precise location. The material that you're putting in the form of a gold jewelry is actually a finished product. Whereas here, the sun's radiation of X-rays is not predictable. It changes at time rapidly. And so you need to know that spectrum and deconvolve this spectrum. And the soil structure, etc., are all very different. You don't even know what other elements are there. So deconvolving that is not easy, but it's done. And today you can actually see many elements directly derived. And out of that, you can actually create maps of distribution. And these are the first set of maps coming out which are direct detection. I mean, in the past, there have been maps produced, but there are indirect ways of doing it. When you look at ion distribution, you're not directly seeing ion. You use some other arguments to actually see, I see ion. Whereas here, you can actually directly derive magnesium, aluminum, and so on. Of course, these are not high resolution maps. The spatial resolution is not very good because of the limitation, and you can only map it when the sun is active. So if the sun doesn't have flares, you will not be able to see it. When Chandrayaan 1 went up, we had a similar experiment, but it wouldn't. It was a time when the sun was very quiet. It was a part of a quiet solar time, and we couldn't get too many. Whereas now we are actually seeing a fair number of it, and the current health of the spacecraft is good that we should be able to do complete mapping. So we can derive chemistry of the surface of the moon, and that is an activity that's currently going on. I think these publications are expected out very soon. But there is this larger interest in lunar science and lunar on the moon today. It's not just the scientists who want to do it. It's not just the nations that have large space programs wanting to do. And so what is going on? And so the global focus on lunar exploration, I think, of course, has science as a key component. In India, we have been still pushing science as a key component. The technology demonstrations. Our landing on the moon on 23rd August, the first and foremost was just land safely, softly, because it's a key technology development. It determines what else we can do on the moon. So that's an important thing. The last attempt to jump or hop was also a technology demonstration. We do these things. But there are also commercial activities. Commercial activities are critical, in terms of, I just now talked about two elements. Titanium is present at fairly large abundances in certain parts of the moon. You can map it using the X-ray lines that you see. So these are critical because that's say for the scientists, it talks about ilmenite as a mineral and formation of melting of the moon, etc. But for a commercial interest, it may be something else in the context of using moon as a base to build products that are required for further space travel. You can't carry everything from Earth to moon. Instead, you actually make some things on the moon, and then you hop from moon to Mars and so on. So there is a lot of interest from a commercial perspective. So in future, you have, very recently, I think tomorrow, there's a Japanese mission going up called SLIM. It is an attempt to land on the moon quickly. It is the previous launch was scrapped, and tomorrow is planned to go. It attempts to land, and that's a technology demonstration primarily. And then after that, we have a program, ISRO has a program with Japan to actually go to the pole, which is a major program, major mission. But there are private agencies doing it. So the companies, Astrobotics, Firefly Aerospace, iSpace attempted, had a problem with again. And so there are many such things going on. So, this is a time when private industry is actually getting into it. I mean, I haven't honestly fully comprehended how are they justifying these things, but other than the fact that all billionaires seem to think today they need to have a space connection, but clearly there is a larger interest in going to the moon. And as I mentioned, the ISRO and JAXA are planning a major mission to the pole, to the PSR region of the South Pole, heavily science driven. The challenges there are quite severe. The temperature in these polar regions is about 100 degrees Kelvin. Okay? Very, very cool temperatures. So there's no light. If you have a rover, the rover needs power. It has to sit in a place where there's sunlight. And there are some regions, a mountain on the pole actually is a good place because for a long period of time, even when the moon rotates, you can get sunlight there. So you have to land on a hill, get your energy there, charge yourself, go down to this PSR region, survive that, and come back if you really want to do anything further with it. So there are numerous challenges. We still do not know how this is all going to happen. And of course, this is a big mission that the Americans are planning globally. I mean, India has also signed the treaty with Artemis now. That is to actually land on the South Pole at a place where there is actual solar illumination. So it actually has to be one of these points of eternal light is what we call it. Places where there's light is there for a long period of time, and they'll do that. And so these are serious activities coming up in future. And of course, China is planning landers and maybe even a human presence before the end of this decade. So there is this global focus that is not just simply driven by science, but by other interests as well. So the question now is, so at a more global level, there are questions being raised that, how can different space agencies that are now working independently at some level, occasionally there's collaboration, work together to really address this in the context of this global lunar exploration. Nations without space programs, how do they participate? This is going to be one of those where, like the early industrial revolution, where those who had access to it exploited to the hilt. But now there is a desire, there is a thinking that we should also take along nations that do not have mature space programs to participate and present their views regarding, in particular, if you are actually looking at creating policies that talk about how space should be explored, how it should be shared, and so on. And so we need to draw global guidelines on this, and it's not easy to get everyone to agree. And this is a challenge that is essential to be addressed if you're looking at a broader involvement in lunar programs. And so that involves sharing of data. And these are real challenges. So just to get you back to the picture, this is the South Pole, can't see from far away, but there is a crater called Shackleton Crater, which is sort of like the real South Pole. And the idea is to really land very close to the Shackleton Crater and do our studies. And roughly, this is where Chandrayaan-3 landed, and somewhere here is where the Lunar 25 mission attempted to land. Yeah, those are the points. So we have used our own data from Chandrayaan-2 to start studying this region, Shackleton Crater, using the infrared spectrometer. Various studies are being done that allows us to really understand the nature of these locations and identify potential landing sites using the radar that we have, the dual frequency radar, to attempt to look for subsurface water. The analysis is complicated because there are many parameters that can actually create strong radar reflections, but all that work is in progress. But when it comes to actual resource utilization, so with these missions that are scientific in nature, we are actually attempting to map out what is there on the moon. And once we know that, we were to share it. Tomorrow, if some company, private company in Italy wants to go there and actually mine the data, titanium, based on Chandrayaan-2 data, we have a bit of a problem here in terms of thinking, can public money that is used to drive a national program share the data for somebody to make money of that in using in a private venture? Such questions have been asked, and so there are questions. So, and there have been early papers that actually talked about how lunar resources can be utilized in many ways. And to take an example, sulfur, which has now become a point of great debate, sulfur has a potential to provide a significant impact because it's sort of like the coal and petroleum, because it can use it to make sulfur concrete. Sulfur concrete may be essential to build on board, it requires no water. And so these are questions that we really need to look into. I know there's a very early papers I've talked about. This is a paper, I think, in the 80s, use of lunar sulfur. Things we didn't pay attention to, but now we're starting to pay attention to because it's going to be a real thing. And there are, to address the guidelines on solar system assets, there are new players in it. So there is a sort of an informal non-profit group called the Moon Village Association, which is attempting to draw some guidelines using a large set of, including people from space agencies, from the public, from the private sector, from countries that don't have major space programs, etc. So they created a group called the Global Exploration Group on Sustainable Lunar Activities, GEXLA. So early this year, we produced, we were also part of that program, and we produced a guideline report that was presented to the United Nations regarding how we need to have specific guidelines on various things, etc. Now, it is now moved on to an operational phase, trying to figure out how will we actually ensure that data will be shared, what sort of agreements will be there, how do I know who will keep tabs on who has gone where, how will you make sure you don't interfere with each other's activities, and so on. When the number of lunar missions and lunar activity increases, some sort of a structure needs to be in place. So these are all very early phase of it, but can actually see the direction which things are going, where you really need to have global governance requirements to really use Moon as a resource for future programs. So, okay, I thought I'll just only have one slide on going beyond the solar system. The astronomy, we had a major mission called AstroSat that was a very successful mission. 2015 continues to operate very well to study the universe, in particular our galaxy and the vicinity and the nearby galaxies in a broad band of wavelengths. That has been quite successful. A lot of people are using the data from that. Aditya L1 is a mission to study the sun and its heating of the corona, as well as looking at solar wind and particles from the sun. That starting in January, we will start observing. And then very soon, there's a launch of a mission called XPOSat, which is actually an X-ray polarimetry mission. X-ray polarization. Polarization of a photon tells you a lot of very interesting things. In particular, it tells you about magnetic fields, which are not easy to study in stellar systems. Magnetic fields are typically studied in a very indirect way. But polarization allows you to do it. And after many years of the only other X-ray polarization experiment that has flown in the early 80s, we now have an XPOSat mission coming from India that attempts to do this. So now, these are all exciting programs. They're large. They take a long time to conceive, to build, to test, and then to launch and to look at data. So I was just trying to pose this question that how can other institutes and universities participate in such a research venture? How could you be part of such a thing? And that is not an easy question to do. Some of your colleagues, faculties here have been looking at this problem. And so the idea of actually creating a consortium of such interested parties who could actually together take a chunk of a program that's coming up in future is something we may want to really look into. While part of the reason is, those who today build these payloads largely in ISRO DOS systems have, they don't have the kind of responsibility you all have. They don't have to teach students. They don't have an academic program, etc. They are fully involved in these issues. They can do that. And so that level of commitment cannot come from institutions that have other responsibilities and other wide-ranging research programs and so on. So the idea of actually, allocating a small fraction, but a meaningful fraction, added together, forming a chunk, is something that we are looking into. So the question looking at is, can we form this consortium space? Universities, and I've been looking at NISER as a potential place, we can discuss it. So we're just putting a piece of paper together to sort of see, can we take it forward? It has a lot of what I call birth pains, so trying to show structure, responsibility, governance, and how we share things, etc. have all already worked out. But it's necessary because that's the only way we can participate in these future programs that are all coming up. New polarimeters, there's a big UV spectrograph being discussed along with the Canadians to really look into exoplanet spectroscopy, looking at the atmosphere and understand its composition, etc. So that's a key area that we can look into. So let me just close with just a few remarks that says, space is an exciting place to do research in science and technology, science and technology. Technology is critical here because it's a technology that allows us to do certain science, but occasionally we demand certain things, scientists demand, and then technology actually walks up to it, and we are able to actually achieve things that otherwise would have been very difficult. But it's an exciting place to do that. And our solar system is certainly a test bed for many things. Those who want to study exoplanets will have to study and understand Earth, Venus, Moon, and so on before you really look at other systems as well. And there is always this incredibly important question about life elsewhere in the universe, which is, tomorrow I'm sure is something that would shake the world if we were to discover something. And so all of this is partly in that direction. And it's very interesting to really ask this question about how NISER could contribute to such a program for a future program. I mean, there are exciting young students here, enthusiastic, but looking for some opportunities and in the midst of their studies. And the question really in front of all of us is to really see what are those avenues we can enable. And we need a lot of fresh thinking. Today, Chandrayaan-3 is a great success for India and ISRO. But there are a lot more things that we need to do, a lot more R&D that we need to do, a lot more optimization of design that we need to do if you want to really to become the larger programs of the world. And that, I think, in my view, requires fresh perspectives that can only come from many other institutions outside the ISRO system. And that is the area where the young minds of this place can actually contribute. So with that, let me stop, and thank you all. Are there any questions I can answer if there's time?
I need some student volunteers. Can anyone please volunteer? Student, just be there to the mic. Or sorry, sir.
Yeah.
Yeah, thank you so very much. And Professor Sreekumar is willing to take questions, or if you want to interact with whatever questions that you have, you'd be more than happy to take. Please feel free. You don't get such chances often.
Sir, amount of we read in the newspapers, amount of space debris is increasing. So how the space explorations or space missions are designed keeping this thing in mind?
Yeah, it's true. The space debris is a major concern with the new large constellation of satellites for internet, etc. That both Elon Musk is doing, as well as OneWeb and others are doing, is a concern. So there's been an effort to really reduce in terms of allowing it to burn as much as possible in a short period of time for near Earth, the low Earth orbiting spacecrafts. For the one in geostationary orbit, they actually are supposed to carry enough fuel to bump it up to a graveyard orbit where it won't harm us in the long run. But the question still is, in terms of the current degree of debris itself is very large. So there have been recent experiments in an attempt to actually grab them, capture them, reduce it, attach tethers that can actually create drag as well as other reactive force that allows it to burn into the atmosphere, etc., are new things that you're looking at. The big spend stages of rockets today is a requirement that you actually bring them back. So very recently, ISRO has also adopted that policy of bringing them back, because recently you must have read in the paper about one that landed in the coast of Australia on a beach, which it is felt may have been from one of the early Indian missions. So the countries are taking some measure in this regard. But the question in the context of the larger involvement of all sorts of people is very difficult. Just to give you an example, the Israeli mission that attempted to land on the surface of the moon carried some living things on board, much against what global regulatory thinking was. So you'll be hard to actually implement some of these things. So debris is a concern. And I think global policies have to really evolve where both there's an attempt not to create excess debris unnecessarily, but as long as the space becomes an area where more and more satellites are going up, and the regulation to really ensure that they burn up or they move elsewhere, if it's not implemented, it can become a major challenge. Yeah.
Thank you, sir. Thank you for this very nice talk. ISRO is very specialized in making these orbiting maneuvers for sending rockets or to save basically fuel. I wonder, when we are thinking of sending man missions to lunar surface, will we follow the same protocol or will have different technology?
Well, it's hard to tell at this stage, but as I mentioned, first we have to get Indians into orbit around Earth. So that is the Gaganyaan program that they're working on. But once that matures, clearly the possibility or the desire to go to moon would be there. And as I mentioned, the Apollo program, when they were designing, they decided not to have multiple maneuvers around the Earth because of the, one, it takes time, which means you'd never know what the sun will do during that time. And two, the trapped radiation belt, the Van Allen belts around Earth are quite severe. Our increasing ellipticity of these orbits that happen with Chandrayaan 2, etc., or 3, means more continuous exposures. And so that is not really a good idea for when humans are in a spacecraft. So most likely the rocket will have to be powerful enough that you can actually go without having to do this. So the fuel demand will be high, but for the safety of astronauts, we'll have to really do that. I mean, even today, I mean, if Neil Armstrong was actually landing at a time when one of the big flares happens on the moon, there would have been very serious concerns about their return. But at that time, they were willing to take risk. Today, we are not willing to take that risk. So if we had a choice, we will zip through, and which means we have to make a powerful rocket that will take quickly people to the location. And then if you're going to spend time there, then you'll have to have some sort of protective mechanism underground where you'll actually seek protection whenever there is a unusual activity from the sun. So these are all relevant things. Even today, going to Mars is primarily stopped because of the concern about how to protect yourself from the solar events. We have no easy way to do that. That's what.
Thank you.
Sir,
yeah.
Could you go back to the slide where you explained the formation of the moon?
I didn't explain actually.
There was this picture.
That picture.
Right. Oh.
Sorry. Yeah.
Right.
This one.
So those small rocks, if this is the case, we should expect small rocks to orbit around the moon or around the Earth, right?
Well, there are many possibilities. They may even have orbited around the moon earlier, but then the question is, over a long period of time, what happens?
Right.
Things stabilize, so gravity continues to act on it, right? So to that extent, even if they were smaller, for example, if the debris that is thrown out did not coalesce into form a single body, but actually forms say 3 bodies, a big one and 2 small ones. That's the kind of picture you are suggesting, correct?
I mean,
Or
it's not so obvious that over a long period of time, all such rocks will just.
they will all come together as a single.
Yes, right.
No, they
right,
may
right.
not have. Not all of it may have necessarily come in that sense. But if you run that picture for long enough period, this happened 4.6 billion years ago. So over long periods of time, it stabilizes to something. Just as today, the tidal locking of Earth's or Moon with Earth happened much later compared to the early phase of it. Earth's rotation has actually slowed down. And so all that has happened much later. So in that period of time, if there were additional debris left, that would actually be lost into the wider solar system in some fashion, either accreted by either of these bodies or may have been lost in some other process. But at the scale of these sizes, we don't really see anything else at this stage. Yeah.
All right. Thank you.
Sir,
Yeah.
you mentioned on the South Pole there is unavailability of solar energy. So why can't we use some other kind of energy like nuclear energy instead of solar energy?
You can, and that's how. There's a lot of lunar missions have already carried plutonium, balls that can actually provide just enough heat to keep things warm. Some of the early experiments from Apollo survived for many months after they left because of the fact that it actually carried radioactive thermal units, RTUs, and so they exist and they can do. But we have not yet worked on it. Actually, not on the rover right now because it carries. Typically, it is very strongly radioactive stuff. So the radiation can damage the core system of a rover or a lander. So what you normally do is this is stuck out on a boom, the end of which you actually keep your plutonium or thorium or whatever. And so all that takes up a lot of space. But in a future program, that would be the right thing to do. What you said is absolutely right. You should really, if you want to really stay there for some time, that's what you do. Some countries are very open to these things. Japan is not particularly keen to have radioactive material. So since the collaboration with Japan, we've said at least a few times, I was also there, we've discussed with them, they're not very keen, but I don't know, maybe as we go along, they might agree, as long as it's not a reactor, it is only just producing enough heat, thermal heat, just like the radioactivity of a planet keeps the planet warm, and drives its thermal cycle. So this is very similar. You just have a concentrated piece of radioactive material providing just enough heat to keep things warm during the cold days of the moon. So that would be the right thing to do, but it has these additional challenges of polluting the place. And if everyone is okay with that, it's all right, but otherwise you have concern.
Sir, actually, I have one more doubt. How Apollo is able to get 380 kg of lunar mass from the moon?
People went there to pick it up.
380 kg.
You
Okay.
didn't know that. And they had a car, 4-wheel vehicle that went 10 kilometers and brought back all sorts of stuff. And when people are there, it's very interesting. There's one case of an astronaut as he was driving back from their location, which was all very precisely defined by the ground station in Houston. He saw something shiny out there and he actually stops the vehicle, tells them, I have some problem with my seat belt. He actually runs off, picks it up, comes back, puts it in his pocket, and then he says, no, everything is okay, and he moves off. Turned out to be a very interesting piece of rock. So they brought back, of course, but now you can also do it automatically. The Chinese mission that brought back 1.7 kilograms was automated. The Russians had done it, the Soviets had done it, but there were smaller quantities, just tens of grams or 100 grams, that level. So it can be done, and maybe someday India is planning to do that.
Thank you, sir.
Hello. Um, so Chandrayaan-3 mission has a payload called SHAPE, which is used to observe Earth as an exoplanet in terms of a few pixels, I guess. So what exactly do we expect from those results? What are we trying to see?
Don't really know. Well, I mean, it's an experiment that was actually originally designed for Mars to look for methane on Mars. And it has a technology that is called acousto-optic AOTF, tunable filter. And so that time I was in one of the groups where we said we will look at this technology in the long run because it provides a filter that doesn't have any moving parts. The filtration happens purely with a radio frequency tuning. So I can tune a radio frequency, sweep it across, and it's like a little filter that moves all the way across various bands, and I can look at the emission through that and derive. So that was the idea. Now, if you use a birefringent crystal, which is what is used to do this AOTF, it actually allows a polarization measurement because there's an ordinary and extraordinary ray coming through this crystal. And you can use this as a way of measuring polarization. So my limited understanding of shape, because I was not involved in that process and they have not revealed a lot of details on it, is they will look back at Earth with shape and look at the polarization content of the reflected solar light and use that as a basis to say something about whether life is influencing this polarization fraction. That's my guess. I could be completely wrong. Lytton might know better. So I really don't know enough about it. I haven't seen directly results from it. So I don't really know much more than that.
So as India operates few launch vehicles.
Where are you? I can't see.
Yeah.
Ah.
So as India operates few launch vehicles like PSLV, GSLV, and LMV now, and developing few more like SSLV and RLV. So what are India's plans for the higher like payload vehicles? Like
so, yeah, I mean, this is a constant debate whether we should build a rocket for very big payloads or should it be for any small. So the greater lift capacity is required for various future missions, including any human involvement that goes beyond the Earth's orbit and so on. So ISRO is working on a heavy lift vehicle. Even the current ISRO JAXA mission to the South Pole will require a 6-ton lift-off capacity, which we don't have right now. So there will be demands to make it, and they are making it. But technology for this is constantly evolving. What is the right technology is a question that we need to really look into. But so keeping in mind reusable engines. So there is a new desire to really look at reusable engines as a way to really save. So that concept of the early rocket designs are changing. So, but I don't exactly know the details. I don't work in that area. But clearly I know there is a program looking for heavy lift capacity for future programs. Yeah.
so, as you said, like India and Japan, the launch program needs like 6-ton capacity rocket. So let's say if India wants to send humans on moon or like beyond, so at that time, like what capacity rocket does
I don't
India
really have a number for you, but if you can, one way to look at it is in terms of the Saturn V. The Saturn V that took the Apollo missions there was so powerful. For a long time, we didn't have anything equivalent to that until they built the new Orion capsule that is meant for rockets and meant for the return of humans back on space. So it's really heavy lift capacity, way beyond that. But I don't have a number for you. Sorry.
Yeah. So on the surface of the moon, we see so many craters, even on the far side, which can give us a proof that there had been collisions from the meteorites or comets during the early evolution. But we see only a very few visible craters on Earth's surface.
Earth surface.
Yeah, that could be because of plate tectonics or the weather conditions whatsoever. But
Correct.
for other planets, even in the solar system or maybe exoplanets, if we see craters, what information can we draw from them about the composition or anything, the presence of water or something like that?
True. So crater counting and crater studies are critical for all planets really because of all the points that we just now said.
Right.
Venus, for example, is a place where one would like to do that. But then Venus has a very dense atmosphere. It's about 100 times more dense on the surface of Venus than here. And so what happens is, the impacting body now has tremendous resistance. It often burns up in the atmosphere itself. Second, Venus has this other problem that it actually seems to be very volcanically active in the sense it actually produces lava outflows that seems to create a fresh surface every 500 million years or so. So it has actually erased the past history. You can only study the recent history. So that's a problem. Now, so you may want to then study that using penetrating radars, if possible, or some other structures, etc. So, but an airless body like Moon is ideal for this. So that way, Moon is so important to do these things. Mercury, they do the same thing. The mission, that messenger mission, and the one that's going, the European mission, Bepi Colombo to Mercury, we'll study. This will be a major parameter that we'll use to derive age of the surface using crater counts. And a lot of effort will go into looking at the craters that you see. Ejecta from that. You know, one of the things that we just recently looking is to see, can you distinguish the impactor composition from the ejected material composition? That would have been a wonderful thing to do. But the current model seems to say it'll all get mixed in so finely it can't really separate the two. But airless bodies are good places to do that. And people will always do that, including asteroid surfaces and so on. You really look for formation or the history of such events to study more about the environment as well as about the body itself.
Thank you so much, sir. Now I would request you to please be on the stage, because this is the day we also felicitate our academic achievers. So there are certain certificates to be given away. I also request our officiating director, Professor A. Sreekumar, to please join the guest on the dais. So we'll move to the next stage of today's function, which is felicitating our academic achievers. So we start with the integrated MSc students for odd semester of 22-23. Semester toppers, first semester batch 2022, Roshan Matthew Philip with an SGPA of 9.68. People in the audience, please give them a round of applause. Next in line is third semester topper, Anish Das with a SGPA of 9.90. Anish is from the School of Biological Sciences. The fifth semester batch 2020 is Prayag Ranjan Sahu with an SGPA of 9.86 from the School of Chemical Sciences. Seventh semester topper batch 2019 from the School of Physical Sciences is Sarabjit Majumdar. With an SGPA of 10. Well, just to reiterate, 10 is the max one can score. From the School of Chemical Sciences, it's Husna AV, again a 10-pointer. Staying with 7th semester batch 2910, from the School of Chemical Sciences, it's Pranay Mohanty, again a 10-pointer. Batch 19 7th semester toppers from all the schools are 10 pointers. Next in line is Rudhi Ranjan Sahu from the School of Chemical Sciences. Chemical Sciences. Yeah. Subject toppers in each school for the third semester batch 2021 from the School of Physical Sciences. It's Hadi Muhammad Sufi with an SGPA of 9.55. Not there. Hadi Muhammad is not there. From the School of Chemical Sciences, it's Om Prakash Swai with an SGPA of 9.82. Om Prakash Swai. So there are joint toppers from the School of Chemical Sciences. It's Om Prakash Swai and Sriram Vignes, both with an identical SGP of 9.82. The celebration of twin continues. From the School of Mathematical Sciences, again we have a joint toppers. A. Rameswar Patra with 9.6 and Sandipan Samanta with 9.6. From the School of Biological Sciences, it's Anish Das with an SGP of 9.90. Moving on to batch 2020, fifth semester from the School of Physical Sciences, it's Sajag Kumar with an SGP of 9.39. For the School of Chemical Sciences, it's Prayag Ranjan Sahu with an SGP of 9.86. From the School of Mathematical Sciences, it's Arav Jugani with an SGP of 8.0. Arav is not there. From the School of Biological Sciences, it's Ayush Panda with an SGP of 9.60. Moving on to the seventh semester toppers, which is batch 2019. From the School of Physical Sciences, it's Sarabjit Mazumdar with a perfect 10. We had twins, now there is a treble. School of Chemical Sciences have three toppers with all of them are all of them are 10 pointers. Husna AV, Pranay Mohanty, and Rudhi Ranjan Sahu. Pranay Mohanty. Rudhi Ranjan Sahu. From the School of Mathematical Sciences, it's Ayanava Mandal with an SGP of 9.33. From the School of Biological Sciences, Nilesh Kumar Das with a SGP of 9.33. The overall batch topper for the odd semester 2022-23 goes to Pranay Mohanty with an CGP of 9.63. Sorry. Moving on, for the odd semester 2022-2023, the semester topper for the CMRP program for the first semester is Mr. Arnab Roy with an SGPA of perfect 10. Moving on to the integrated MSc PhD students for that particular semester, the semester topper for the batch 2022 is Atal Swati Patra with an SGPA of 9.56. And she shares the honor with Ipsita Paricha with an identical SGPA of 9.56. So the overall semester toppers are from the School of Chemical Sciences. Subject toppers, batch 2021 third semester physics goes to Mr. Tanmay Poti with an SGPA of perfect 10. For biology, it's Akshat Bhanu Dharmani with an SGPA of 8.40. For the School of Chemistry, we have Atal Swati Patra and Ipsita Paricha, SGPA of 9.56. Ipsita Paricha. Batch 2022 first semester mathematics, Mr. Arijit Mahato. Batch 2022 first semester physics, Mr. Swarup Kumar Giri with an SGPA of 9.40. Moving on to the integrated MSc students for even semester, the semester toppers are Ashlyn Thomas, second semester batch 2022 with an SGPA of 9.68. For the fourth semester batch 2021, A. Rameshwar Patra, SGPA 9.90 from the School of Mathematical Sciences. Sixth semester topper, batch 2022, Deepak Kumar Mishra from the School of Physical Sciences with an SGPA of 9.55. For the eighth semester batch 2019, there's again a treble and it's chemistry. Chetan Kumar Prasad, SGPA of 9.83, followed by Husna AV 9.83, Pranay Mohanty 9.83. So two of them, Pranay and Husna, were part of the same treble for the other semester as well. Moving on to the subject toppers for each school. Fourth semester batch 2021 School of Biological Sciences is Samiksha Kar with an SGPA of 9.67. For the School of Chemical Sciences, we have a tie. Om Prakash Swai with an SGPA of 9.18, and Sriram Vignesh 9.18. Consistency, thy name. The same two with the topper in the first semester as well. School of Mathematical Sciences, it's A. Rameshwar Patra. School of Mathematical Sciences, A. Rameshwar Patra with an SGPA of 9.90. Mathematics. School of Physical Sciences, 4th semester batch 2021. It's Agnay Rajiv with an SGPA of 9.36. Moving on to the 6th semester batch 2020 from School of Biological Sciences, it's Advita Sharma with an SGPA of 9.25. School of Chemical Sciences is Prayag Ranjan Sahu with an SGPA of 9.45. School of Mathematical Sciences, it's Arav Jogani with an SGPA of 7.60. Arav Jogani, it's not there. Okay, so moving on, School of Physical Sciences, 6th semester. Topper is Deepak Kumar Sharma with an SGPA of 9.56, 9.55. Sorry. For the 8th semester batch 2019 from the School of Biological Sciences, the three joint toppers, Amisha Aparupa, C. Vaishnavi, and Shubhanjali, all with an identical SGPA of 9.33. For the School of Chemical Sciences batch 2019, Chetan Kumar Prasad, Husna A.V., and Pranay Mahanti. Again a treble. And they're from the School of Chemical Sciences. Trebles. School of Mathematical Sciences, it's Ayanav Mandal and Gargi Biswas, both with an identical SGPA of 9.67. For the School of Physical Sciences, for the 8th semester batch 2019 is Abha Vishwakarma with an SGPA of 9.50. And the overall performance for the entire year, for the semester, across all the schools goes to Pranay Mahanti with an overall CGPA of 9.66. Overall topper for the batch across all the schools. Moving on for the CMRP students for even semester 22-23, semester topper, second semester, Mr. Arnab Roy, with an SGPA of 10. Arnab, please stay on to collect your overall performance award with a CGPA of 10. Overall topper of the batch. Moving on to the integrated MSc PhD students for even semester. The semester toppers are batch 2022, Leepika Bardhan from the School of Chemical Sciences. Subject toppers for each school, batch 2021, fourth semester physics, Tanmaya Poti with an SGPA of 9.80. For the second semester biology, it's Mr. Akshat Bhanu Dharmani with an SGPA of 9. For the second semester chemistry, it's Ms. Lipika Bardhan with an SGPA of 9.83. For the second semester mathematics, it's Arijit Mahato with an SGPA of 9.40. The second semester physics, it's Swarup Kumar Giri with an SGPA of 9.60. For the overall topper for the batch, it's chemistry's Lipika Bardhan, who is not here. So that marks the end of this award ceremony. We thank you so very much for gracing the occasion. I also request our director, Professor A. Srinivasan, to kindly hand over a token of appreciation from the entire NISER family, a small memento. Thank you so very much for gracing this session. So this marks the end of first session. Guys, please don't go anywhere. We'll start the second session. Please stay back. Unless there is an urgent need, please don't leave. I'll put people out there who will not allow you to go out. So we will have our cultural program in 5 minutes. Please stay on. बाहर कोई नहीं जाएगा. बहुत मुश्किल से अंदर आए हो, बाहर जाने नहीं देंगे.